Yeah, good afternoon, Manimaran sir.
Good afternoon, sir.
Yeah, good afternoon, all the participants, and welcome back to the day two, the session three. And again, the Manimaran sir will continue the session now. And shall we share the screen, sir?
Sure, sir.
Yeah, I'll
I'm just
stop my.
I'll just make some. I'm just making some connections
Sure, sir.
for that lab over there.
Okay, sir.
So give me just 2 minutes.
Sure,
I'll
sir.
just.
Once it is completed, let me know, sir.
Yeah, sure, sure. Give me 2 minutes. I'll close it.
Sure, sir. No, not an issue.
Hello, sir.
Yes, sir.
Sir, is it visible?
Yes, sir. Your screen is clearly visible, sir.
Okay, great.
Yes.
So, shall we start?
Yeah, yes, sir. You can start, sir.
Fine. Very good afternoon to all. Uh, as what we have seen in the morning session, we will be discussing about how we can use this hardware for different labs. So, I actually, if you see, I have a hardware connected with me, which is a smaller version of an Elvis hardware. So I connected a few logic gates with this so that we can use for a few of our lab purposes. So I'll just open the function generated part of my hardware, which means a single hardware which has all these items. So I have a function generator. I'll have oscilloscope. Now I'll be having two devices. So we'll have it as a virtual instruments. So virtual instrument is something as uh, along with a computer, we will have a software module and a hardware module. So totally three things will be there. So if you see, these things are called as virtual instruments. This is made by a software piece where a hardware is connected in it, so that when I say start generate a signal, it will generate a signal. So this oscilloscope is again the same thing, but instead of generating a part, this is going to acquire a part over there. So now if you see there, so I have a function generator. I have connected my wire to analog output channel 0. I have connected to my signal to analog input channel 0. So when I run my program, what happens here is it continuously try to acquire some data, but it is not the actual data, because I have not run my function generator, so the data won't be the right data. So it is giving something as an empty one. So now if you see there, when I start here as a function generator, I run my function generator, I'll say to triangle. 1 minute. Yeah. So now if you see, this is a real signal. So when I say here as a 100 hertz, I'll say auto scale. So now do you see I'm getting as a 100 hertz as a triangle. When I say sine, it changed to sine. So now here I'll say a peak to peak as 1. So when I say peak to peak as 2 volt peak to peak, units as 1. So now you could see there the signals are proper. So now if I want to see the edge 1, so now if you see there, this is something as a trigger what we have provided for it. I'll say immediate signal, so I'll get the continuous one. So earlier, if you see over there, when I'm trying to do first, I could not get the data because the signal is not coming from the actual hardware. Now the signal is coming from actual hardware, because when I stopped function generator, I don't have any data. So I run here. This is not a simulation, because if you see, when I remove wire from analog output, there is no data. Whenever I touch something, you could all see some noises there. When I connect back to the channel, then only you will get it as a. So now I'm connecting the signals. So now do you see that when I connect my signal back to it, I'm getting the data there. So this is not a simulation, because when I change to square, when I change the duty cycles there, so now you could see there is a difference in the duty cycles of the square signal. You could see there. For example, when I say 25, it will be a different one. So you could vary how exactly your pulses has to be generated, or the signals has to be generated, that you can easily define with your module here. This is programmatically which we are doing it. So now when I say sine, so now I want to say sine over there. So I'll say stop. So when I say sweep, in the sense it continuously sweep within the range of starting frequency to stop frequency there. So do you see that it is continuously increasing there? So this would help us in the place where we use for our circuits. So now I run my program. So continuously it is running with this. So when I change these elements, so do you see over there, these things are happening with my hardware. So this is a real data, whatever I have. For example, when I say 5K there, this is a 5 kilohertz signal. It's a pure data. So when I change my amplitudes over there, this is the real amplitudes. What do I get there? So this is a 50 kilo samples. When I keep on increase my sampling elements, when I try to sample it a little higher, when I try to sample it a little higher, do you see there? I'm sampling it at 200 kilo samples per second. If I use an Elvis hardware, I can go up to 400 megahertz there, because this is a lower version of my Elvis hardware. So now, for example, if you see there, uh, uh, I have a diode and I have a resistor. Yes, I try to build a small rectifier circuit so that we all could understand how this circuits are behaving in it. Yes, so give me a moment, I'll just do the connections and run it again. So now, is my voice audible?
Yes, sir, it's audible.
Okay, fine then. So now, if you see there, I still have a function generator oscilloscope. So now I have a diode connected with me, and I have a resistor also with me there. So what I'll do it is, I connect the function generator input to diode input line. I am connecting the function generator reference to the resistor end. I am connecting one wire to the oscilloscope input from the diode output end, other end. So now I run my oscilloscope, I run my function generator. Do you see over there? So the signal, whatever I'm generating here, I'll keep it as 100 hertz. I'll keep it as 2 volt peak to peak. Okay, let me stop this. 1 minute. Function generator, oscilloscope, sine. Okay, fine. So I'll see the output end. Yeah. So now I try to keep 3. I'll try to keep 50. So now we are seeing the output signal. So now I want to see input signal also. So what I have to do it is, I have to enable one more channel. So I'll connect positive to the oscilloscope channel positive there. I connect the reference to the resistor points there. So now what I'll do it is, I'll enable analog input channel 1 as well. So now we will be getting 2 different signals. So let me disable channel 0. Okay. So when I enable channel 0, I think there is some ground issue here. Okay. 50 hertz, 3 volt auto scale. So when enable both the signals, we should get okay. One volt. I think there is some wire connection issues. Fine. So now we are getting forward biased. When we turn the diode, when we reverse the diode, we'll get the reverse bias. So the similar way, what you can do is we can enable both the channels. For our information, we can see with that, with the help of connecting two signals. For example, let me stop. I'll stop function generator. So now, if you see over there, we have two channels. So where we can connect function generator output to channel 1. When we run here, when we run oscilloscope, the same data we are getting. Ground reference will take through the ground reference there. I'm enabling channel 1. So here we have a half a rectified signal. The same way we can build for other signals also. So this is one experiment. So very basic experiment where we can do for different labs. And I have one digital experiments we have, logic gate experiments I have. So I have 7408, 7432, and 7486. So connected with me. So where I give power supply. I'll connect ground line to the line number 7. I connect power supply to the line number 14. So now this is all for your function generator oscilloscope. So now I take something as a digital writer. I take digital reader. So both these programs are not running. I stop them. So now 0 to 3 lines I use it for write, 4 to 7 lines I use it for read. So I run this program. Okay. So we have to choose a device number 2 there. Device number 2. So now here I have connected my inputs 1, 2 as an input, 3 as an output for 7408. So I make 1 high, 2 high. Do you see the 7 become high there? Because output is connected to 7. So when I remove this wire, I'll not get output because this is a real data. Unless until both of my logic gates are high, I'm not getting output. So this is for 1. So if we have multiple, we can use the same over there. So now I'll use the same connections I'll use for 7432. So what I'll do it is I give 1, 2 as an input. I'll give 1, 2 as an input there. So now what I'll do it is I connect it to 3. So now I have high. So when any one of my inputs are high, still I get the output high. So if 2 is high, it is high there. If 0 is high, it is high over there. When both are high, the output is still high in there. So now if you see there, it's a very simple what we are doing it. So we have 7486 also we have. So for 7486, what is the pinout diagram in it? If you see over there for XOR gate in it, I have to give the same way. So I'll connect it to the ground to the line number 7, power supply to 14. So now I give 2 inputs to 1 and 2. So here I have an output to 3. So now I give 1 high, so it will be high. I'll give another line high, it will be high. When both are high, the element will go 0 there. The output will be 0 because it goes to the sum. So we'll have a carry elements also will be there. So the same logic we can do with our normal regular labs, whatever we do with this. See, instead of your physical trainer kits, what you have. So here we have a hardware connected with it where we are making use of the analog in analog output lines of the DAC card. Sorry, here we have analog in analog output of the DAC card and we have a digital in digital output of the DAC cards to use this program. So now if you see over there, the experiments are very simple. See, whatever we do with this, so for example, whether it is a digital read or write, or very simple thing which if anybody has, this hardware, then they can start do their lab work then and there. So this is one part. The other one is obviously the other places we'll be in a lab under the supervision of the faculties and where we do our regular lab works there. So now if you see in this, the programming part also remains the same here. So whatever we do with this program, so however we make logics in this, it all remains same. For example, now I'll go to LabVIEW here. So I'll go to a VI. Before I start with LabVIEW programming, does anyone have any queries in this analog circuits as well as digital circuits, digital logics experiments? Do you have any queries? No queries? Okay. So now what I'll be doing is I'll just go to LabVIEW to do a program for it. So for example, first let me start with this digital part because the circuit connections are there. So you can easily do with that. So I'll go to Express, Input DAC Assistant. So these DAC modules will help us in doing our programs with the hardware so that we can directly find out which module we have, how we are wiring it, from where to where we are wiring it. Everything we can define it by programming here. So I'll go to generate signal, digital output, line output. I'll choose my DAC card, second module. So I'll be choosing two outputs line here. So these are the two output lines. So I'll say OK. So I have a Boolean push button. I have one more push button there. So for example, let me say it as X. Let me say it as Y. I have an LED indicator. I'll say it as Z. So now I have this X and Y there. I combine them together so that I can send it to the single element. So I want to see the output. So I need to acquire the digital input line there. So now we are generating two lines. So we are taking this. So now I'll take one more DAC for acquire digital input line, which is connected to line number 7. So this is the one which I am going to get. Yeah. So now if you see there, so I have combined the two Boolean inputs that I convert to data, so which I am reading over there. So I want this code to run continuous. So yesterday you all have seen how to run a code continuous. So we'll be using a loop. So the same way I'm using a loop. I'll add a minimum time delay there. So now when I run here, okay, I'll say stop. Oh, sorry. Do you see here this program is running there? So I'll say stop them. I stop both the places. Then I come and run here. So now here, if you see when I say high, for XOR gate, any one element is high, it is going. So when I say both are high, it is going off. So the same thing we can do for OR gate as well. So now in this, when I run here, so any one is high, it is high. So now what you can do it is, you can have numbers also. If you want to define, instead of this, you can define numbers also there to check with your truth table. So we have 0, 1, 0. So based on that, you can convert it. So how exactly you are giving your values? So based on that, you can change accordingly there. So this is something as your number based, your truth table wise, you want to see the output, or the Boolean wise there. So here we will be converting a number to a Boolean and we'll be sending it. That is the only thing. So this is one way. The other one, let me save this VA. I'll save it as a AICTE V3 NCET. So I'll say it as a digital electronics lab. So the place where we do a lot of logic edge designed experiments we'll do there. So when I create one more new VI for it, I'll try left and right. So now for the, I could say something as a analog, or I could say it as a for digital circuits or whatever we plan for it. So we can easily do with this type of connections and we can go on. So now I have a diode and resistor there. So if you see how we will be programming is we'll be doing the same, but instead of choosing digital lines, we will be going for analog lines there. So there you can define how many number of samples you can take. So how you can save your data to an element. So everything you can define with that. So for example, if you see, I'll generate through analog output channel 0. So now what I do is I go to the same DAC support assistant. So first I'll generate a signal, analog output, voltage type of output through the line AO channel 0. So here do you see that I can define how many number of samples I need to generate, whether I need to continuously generate a signal or I need to generate only less number of samples. I can define them there. So whereas in the previous one, when we use a function generator oscilloscope, you can't control the number of samples to be generated or acquired. So here I define what kind of signal to be generated. So I define, so what is the frequency, what is the amplitude there. So I create a control for it. I want this to run continuous. So I create one graph indicator to see the signal. So now I want to read my data. So I need to acquire them. So analog input, I'll say voltage through analog input channel 0. Here I'll acquire more number of samples. So now I have one signed data and one acquired data there. So I have a stop button to stop the code. Amplitude, frequency. I just replace them with a knob so that it would be easy for me to choose it. For example, I'll say 100 Hertz. So now if I run here, so now this is inverted. So I change the diode. So now this is a frequency of 10. So now when we go for higher frequencies, we could see them. So now if you see over there, whenever it is generating one, so I have only the positive peak there. So we can add more higher samples. So we could see that. So out of 2 volt, I'm getting only 1.4. So 0.7 is being cut off there. 1.3 nearly 2 volt. 0 to 1.3 there in it. When I say 1, it is of only nearly 4 or somewhere there. 0.65 near to it, it got cut off. So if I want to see both the signals, then I will be connecting one more wire to it, to the additional channel of it. So now what we do is we need to add one more channel to the equation part. I'll add a channel voltage through analog input channel 1. So here we'll be getting only one plot. So whereas here we'll be getting two plot. So now I'll say stop. Could you see there? So here I have one white color, the other one. So when I run here, could you see over there where I have the details there? So where it got cut off once with that. So probably when we increase, then we could get little faster signals there. So once we go for these samples, more number of samples, then we'll be losing many, I could say it is samples over there. So it's a very less sample, so we are getting little sharp edges or curves we have there. So this way you can easily tell them the difference between your original signal as well as rectified signal. So you can show them easily to work. The same also you could show with this, but here the problem in it, you cannot show them as a part as so now I'll show here. So one is rectified signal, one is input signal. So when you want to show them together, this is how both will look like. Oh, sorry. I stop here. So the how you are looking at this, the same way you will be looking over there. So this is one. So it is going beyond one over there. So the voltages, the differences you could see with that. What is the maximum difference? Here also I am getting peak 1.3 or 1.4 volt in there. So 0.7 I have gone out. So even in lab view also, we are getting the same thing. So almost nearly there. So zero point 0.7 or 0.65 has been ruled out there in it. So any queries? So you can easily teach your labs. You can easily teach your concepts with the help of these DAC cards, with the help of these modules. Sorry. So if you have any queries, just let me know so that we can discuss about it. Any of your faculties are handling uh, electronic circuits or linear integrated circuits or digital electronic circuits in this semester? Okay, fine. So now probably we could discuss about uh, different lab practices, what we can do with this hardware. See, for example, if you look at here, when you do your real audio signal or your speech signals also, you can easily show with this. For example, let me go with my signal. I'll connect analog input, analog output as an analog input over here. I'll connect the ground lines to the ground line there. I'll save them as half a rectifier. So when I create a new signal, so what we can do it is, for example, I'll ask my hardware to generate some signal there. So I tell what kind of signal you need to generate. I create a graph indicator for it. The same data will be generated through a DAC system. I define the frequency. I create control for it. So as well as I need to acquire my data. This also in samples. See, for example, whatever I generate here, I'm not going to say it as I'm not going to rely on the signals what I'm generating here. I'm going to calculate based on the signal what I receive from here. So for example, when I run here continuously, I'll add a while loop there. I create a constant, I'll say 100. So I run, stop. So I'll just close them. Yes. So I run here. So now if you see whatever signal I'm generating, I'm getting here. So now in this, I can go up to any frequencies here. I can easily generate and acquire in this. For example, if I want to work with different frequencies, or I need to understand how do I find out what is the frequency of this, I need to verify them. So how could I can verify that? So for example, if you see there, I have something a signal analysis where I go for the spectral measurements. So I want to see the FFT of it. So I'll choose a power spectral density. I'll say linear. So here I see a hanging or hamming window, black man. Yes. So if I see a rectangular window, I want to choose none. So by default, it will take a rectangular window there. So in morning, I have shown you in the measurement live web-based applications, you have that mathematical and FFT operations, right? The same operations we are doing programmatically here. So I create a graph indicator. So where this shows me FFT of it. So this is the one. So what signal is it? It's been identified by the FFT here. So this is supposed to be a frequency. This magnitude. So when I run here, so here. So for as a sampling rate, so maximum up to 500 hertz I could see there. So when I go here beyond 30, 40, 60, so 100 hertz it is. So 200 hertz, 300 hertz, oh, 500 hertz it's not possible. 500.1 it is. So when I say 400, I could see the 400 peak there. So here I could easily play around with the signals there. Actually, if you see that after once you acquire data from there, this is what the parameters that we all will be using. So you could easily match your classroom experiments with such kind of things. So probably what we could do it is we apply a filter. So I'll say a band pass. I'll say 200 to 300, or I'll say 250 to 300. $200 to 300. I'll say OK here. So this is input signal. This is filtered signal. So one part which I'm going to say is when I say 250, this is the maximum where I could get all my data. So now if you see there, maximum my amplitude is 1, minimum is -1 there. So now when I change it to 100 or 50, do you see signals are there, but only their magnitudes are going down. So how we could prove is, I'll try to take the same FFT part to my filtered signal as well. So when I say 100 also, there will be a peak for it. So this is BPF FFT, band pass filter FFT. Hope it should be visible to all. So I run here. Do you see still I have a peak? My normal FFT also gives me here 100. The filter FFT also gives me 100. But in time domain, you see that I don't have any signal there. Actually, here also I don't have any signal. If you see, both the magnitudes are very, very low when compared to each other. So do you see that the band pass filter magnitude is very, very less. So when I go here 200, so when I say 210, yes, so 210, 250 is the max there. So now I remove this as an auto scale Y. So now when I try to increase here, it keeps on goes down. So when I try reducing it, it will allow my data there. So less, it will go down there. So this is something we are working in a simulation to teach how a filter behaves here, how a filter works there. So now, for example, I increase my sound system volume, filter and FFT. Now I'll create a real application for it. For example, I'll go to graphics and sound, or I'll go to Express, input, acquire a sound. I can acquire a sound from my system through the inbuilt speaker. I can acquire through 5 seconds. Now I create control graph indicator. So now if you see over there, when I run my program, for 5 seconds it will acquire, it is acquiring the real data and it will replay later. But it is not replaying because we made it to only acquire. So now if you see here, when I take Express output, play a waveform, this is through my speaker. So now what I'll do it is, I want this data to be spoken by my PC. So now I run my program. After 5 seconds, it will automatically speak. Whatever I'm speaking, it is something as a record and playback. 5 seconds, it will automatically speak. Whatever I'm speaking, it is something as a record. So this is a record and playback. Now I'll go to my previous program. I copy the same filter FFT part. I'll show you somewhere in between here. It means we all listen to what is the actual sound is. We'll apply a filter there. So whatever signal that I'm getting there, I apply a bandpass filter. That bandpass filter data, I'll play through it. So now I run my program. So this is the actual signal. This is a filtered signal. And this is the FFT of it. So that I'll come to know what is the signal that I have spoken out and what is the frequency of it, how the time domain signals looks for both the pictures I have here. It is a stereo input, right? Microphone. So now it is going to acquire for 5 seconds and show me the details here. Now it is acquiring. So now do you see there the frequency elements? So now when we zoom and see the portions, we could come to know how exactly our signals are, where exactly it is lying. So it is showing only within the range of 200 or somewhere. If I see where the peak is, so the peak is somewhere as 222. What do we have? So it is somewhere within the range of 222 and 255. So it lies in the range of 222 there. So this is the maximum peak what we have got. So this is the signal what we have, and after filtering, this is what we have in it. So now if you see there, we can easily take it out and we can allow it things over there. So this is something as a real data. So what we will be doing is, in place of our hardware acquisition, after we take our signal with noise, we'll applying our filter portions here. Our filter portions will come here, FFT block will come here. So only thing is, after acquisition, we'll be doing lot of our programming parts here. Yes, I hope this could be little useful for you in your regular classes when you plan to teach some concepts with the DAX sessions. Do you have any queries? So do you have any queries related to DAC interface with your lab sessions? So probably we can discuss with that. So nobody has any queries, sir?
Yeah, dear participants, if you have any queries, you can ask sir regarding your doubts.
Hello, sir.
Yeah, hello sir.
How exactly you and your team are planning for this lab, sir? This particular labs, whatever is shown as a LIC lab or digital electronics lab. So how you are planning for it? You have a trainer kits and you use with that, or how it is? Hello.
Hello sir.
Audible, sir?
Yeah, it's audible sir. Yeah, it's sir.
I have a doubt how your regular lab sessions will happen. So whether whatever is shown as a digital electronics or your logic gates programs or your half a rectifier. So
Yeah,
how
it's
you will be doing it with the regular
clearly.
labs?
Yeah, even we have a hardware, no sir. So directly through the hardware only, through the digital kits, we are going to perform it, sir.
Okay, so you have a trainer kits for it.
Yeah, it's
Okay. I think then we can wind up, sir. If most of the people know have queries in the sense, we can wind up. No issues.
Dear participants, if you have any queries, you can ask us now, or else we'll wind up with the session. So we hope that there are no any queries for all the participants. So thank you, Manimaran sir, for your wonderful presentation, and clearly the practical one which you have shown related to the digital things which we have in electronics. So thank you very much for your presentation, sir.
Thank you, sir. Thank you very much.
Yeah.
And thank you everyone for
Yeah,
attending the sessions.
Yes, sir. Sure. So thank
So
you all.
be safe and stay safe.
Yeah, thank you, sir, and even you also.
Yeah.
So thank you all the participants, and today we are winding up with the session, and again by tomorrow at 9:30 we will be having the day 3 session. Thank you everyone.